Okay, so we have to prove that this determinant is the thing on the right hand side. So every row is a GP basically, and over here you have xj minus xi, where j is bigger than I, and I and j are in 1 to n in that range. So this is gonna contain all kind of combinations that you can get. So like for I equal to 1, you'll get x2 minus x1, x3 minus x1, so on till xn minus x1. For I equal to 2, x3 minus x2, all the way till xn minus x2, and so on, right? So let's do this inductively. Our base case would be when this is a 2 by 2 determinant, so you just have 1 x1 1 x2, and that's equal to x1 minus x1. Yeah, and that satisfies this expression. Sure, it's the same thing as that expression. Now let's do the induction step. So what we're going to assume um, is that x, so like, okay, we're going to start with 1, of course. So 1 x2 x2 square all the way till x2 power n minus 2. So not n minus 1 but n minus 2. And then here you got like 1 x3 x3 squared all the way till x3 power n minus 2, and so on. All of this in the determinant, and this is gonna go on till xn, of course. So 1 xn squared all the way till xn power n minus 2. This is just the product, where 1 less than or equal to I less than j less than n minus 1 not equal to, sorry, so it's not equal to n minus 1 of xj minus xi. So that's what we'll assume. So now what we want to do is go from this determinant to that determinant, basically figure out what this determinant is given this equation. Okay, so what we can do is we subtract the first row from every other row. So you'll get this thing 1 0 0 0, so on, n of these so n minus 1 zeros, and this is a 1 over there. And then you will have this x1 squared all the way to x1 power n minus 1. And first you'll get x2 minus x1, then x2 square minus x1 square, and so on, right? And then over here you'll get x3 minus x1, x3 square minus x1 squared, and so on. And of course you can factor out x minus x1 from this expression and this expression, and so on, so like from the whole row itself. And you know that this determinant is the only thing that matters, because all these are zeros, so it doesn't matter what their cofactors are. Multiply by this element, you will get 0 anyway. So that means this determinant is the same thing as this determinant, which is now an n minus 1 cross n minus 1 determinant, right? And in fact you can like factor out all of these things, x2 minus x1 and stuff, so you'll just take that out. In fact, I'll put that in a product. So it's the product of xj minus xi. I shouldn't say xi because there's only one xi really. So xj minus x1, right, where j goes from so you start off at 2, right? Okay, so 2, and then you end up at n. Okay, this product thing times this determinant. So first you take out x2 minus x1, you just get 1 over here. You'll get x2 plus x1, usual GP formula, and then x2 square plus x2 x1 plus x1 square, and so on, right? Eventually you will get the last GP. So this was x2 power n minus 1 minus x1 power n minus 1. So here you will start off at x2 power n minus 2, and so on, and similar stuff over here. Okay, so notice that this thing is a degree n minus 1 polynomial in x1, and this would and this complete determinant would of course be a degree n minus 1 polynomial in x1, because this is our highest term. And then for each of these elements, the cofactors do not have any x1 in them, so this would be our constant term. So like 1 times this determinant, that's our constant term. X1 times determinant of all of this stuff, that's our minor, of course. That negative of that, of course, that's our constant. Okay, that's our coefficient, sure. And for x1 squared, you would just have this minor, right? Those are coefficients. So eventually you're going to end up with x1 power n minus 1 as the biggest term. So this is the degree n minus 1 polynomial, and this is also a degree n minus 1 polynomial, which means that this whole thing must be independent of x1, because if it's not, Doesn't make sense, right? Here you have a degree n-dimensional polynomial, this is another degree n-dimensional polynomial. This must be um you know independent of x1 or something like that. I mean, at least it cannot be a polynomial. But guess what? Over here, all you're gonna do is like multiplication and addition. So this will in fact be a polynomial in x1, right? So if you were thinking that maybe this is some function, okay, this polynomial and this polynomial are not actually having the same factors, in fact, then yeah, this could be that this is not a polynomial and it's still dependent on x1. But we know that it's only made up of multiplication and addition, and because of that it has to be polynomial. So what we can do is just put, you know x1 equal to 0, because this will be a constant for any x1, right? You don't believe me? Do this thing. Subtract x1 times the first column from the second column. You just get x2, x3, so on. So like that column is now constantified, if you would call it like that. Then subtract x1 times this column from the next column, so like this middle thing will be gone, and then over here you got all these x1 squared stuff, so that can be easily taken out by multiplying this thing by x1 square and subtracting from here, right? And stuff like that. So you can easily prove to yourself in your mind that sure, this, like all these columns can be constantified. I don't know if this is a correct term, but yeah, constantified and constified, well, whatever. So eventually you'll get rid of all the x1 things over here, and you'll just get something that's independent to x1, right? So instead of doing all of that, what we can do is just get rid of all the x1 stuff right away by putting x1 equal to 0, because it doesn't matter what value of x1 you put, it's a constant. So might as well just put x1 equal to 0, and that gets rid of all of this. So you just get this x2, x2 squared, x2 cubed, so on. Over here you just get x3, x3 squared, x3 cubed, so on, and till what, x2 power n minus 2, right? Yeah, I mean, look at that, it's for n minus 1. So now the gp would be having n minus 2, because yeah, sure. And similarly over here, x3 power n minus 2, x4, and yeah, you get the thing. That's our determinant. And guess what, we already assumed what this determinant is going to be, right? We assumed that this thing is equal to this expression on the right hand side, so we can just plug that in. So this is the product of xj minus x1, where of course I'm not going to write all of this, but we're assuming that j is bigger than 1 and it's running over 1 to n, right? 2 to n, because it's bigger than 1, but you get the thing. Okay, and that times this product, once again, xj minus xi, where I is not equal to 1. So here you have oh, okay, I should have written this, in fact. So 2 to n minus 1, because there's no x1. Seriously, there's no x1, so how can you even do that? But yeah, that's the thing. And I shouldn't say it's less than n minus 1. It should be less than equal to n, of course, because this is there. Yeah, that's the thing. Right, so this is still okay. The range from 2 to n is still containing n minus 1 numbers, right? So this is a smaller matrix or smaller determinant. So it's a n minus 1 cross n minus 1 determinant. This is an n cross n determinant, right? Makes sense. So we can just plug this expression in, which I'm going to write like this. So it's the product where I is not equal to 1, j is bigger than I, of xj minus xi, right? So basically, yeah, combining these two, you just get the final product, that the product where I is 1 is also included and j is bigger than I. Notice over here j will of course be bigger than I, so because j starts off at 2, I should just put that j is starting off at 2. Is this one equal to n, and over here as well, right? Makes sense. So now combining these products, you just get j bigger than I, xj minus xi, where the limits are the usual thing. So yeah, here you go, we proved this statement in that case. Sure. So I'll also show you a little bit of application of this result that we got. So suppose you are given n points in a 2D space. So you are given x1, y1, x2, y2, so on, and you want to find a polynomial in x which passes through all of these points, right? So when will you be able to figure out such a polynomial? Are you always able to figure out such a polynomial, right? That's our question. So we are assuming that all of these xi values are distinct, because if they were similar, then you of course can't find a function which has like two values at the same x value. That doesn't make sense. It's not a function. So all these x values must be distinct, and then in that case, can you actually find out a polynomial every single time? Well, yeah, you can, and we can easily prove that because we can write this thing. So assume that y of, instead of y of x, I'm going to say f of x, that's our polynomial, that's equal to this thing. It's c naught plus c1x plus c2x square, so on till cn. And say you are only given n points, so that means our polynomial will be having n minus 1 degree. Why is that? Because n variables and equations, you'll understand what I mean when you see what I'm doing. So this will be cn minus 1 x power n minus 1, right? I mean, all of these are basically our variables, right? The usual way to figure out a polynomial passing through some points, say for example 3 points, would be, assume a polynomial, right? Assume that its degree is unknown, right? So initially you start off with an unknown degree, of course, but then you you realize that, okay, so if you got, let's just say 3 points, then you can write this thing y1 equal to c naught plus c1 x1 plus c2 x2 square, and so on, and then y2 equal to c naught plus c1 x 2, right, plus c2, should be x1 over there, x 2 squared, and so on, right? And y3 equal to, yeah, the same stuff. So over here, c0, c1 and c2 things are variables, right? y1, y2, y3, x1, x2, x3, these are known values. So this is basically a system of equations, and it has 3 equations and a bunch of variables. How many variables do you need? You only need 3 variables to uniquely figure out that polynomial. So you will not have all these c3 and c4 stuff. You will just restrict yourself to this. That makes sense, right? Yeah. And so the question really should be, can we figure out some n minus 1 degree polynomial which passes through all of these points, right? That should be our main question, because then that will be unique, right? Yeah. If we can find it, it's unique. If we can't, we can't. Can it be that you don't actually have like a unique polynomial and there are like multiple polynomials? Sure, you can have that, because it's in the end a system of equations, so it could be it's consistent, and at the same time this determinant is not zero, so you have like a bunch of solutions. But our main concern is, can you find a unique polynomial of degree n minus 1 given that it passes through all of these points, right? So after resetting our, like rephrasing our question a bunch of times, the final question that we get is this thing, and let's see, can you actually do that? So for example, in this 3 by 3 case, you can write this vector y1, y2, y3 equal to 1x1 x2 squared 1 x, it should be 1 x2 x2 squared 1 x3 x3 squared stuff, and that times c0 c1 c2, right? So then this question is basically asking, is this determinant 0? Because if it's not 0, you can invert this matrix, and that would mean you can figure out c0 c1 c2, right? So a unique quadratic polynomial that's going to pass through these 3 points, right? And with this expression that we got, it's easy to see that if xj is not equal to xi for any j or I, which are of course unequal, then yeah, you're done basically. That this thing can't be 0, which means that a bunch of these things multiplied is also not 0. So you can actually invert this matrix, which means you can figure out C0, C1, C2, and that's going to be a unique solution. And yeah, you basically get a polynomial. Nice. So the only case when this determinant will be 0 is if somehow, xj and xi were the same, but then yj and yi must also be the same, which would mean that you have two repeated equations, right? And in that case, yeah, you will be able to figure out multiple polynomials, because instead of having uh, three distinct points to pass through, you only have 2 points, so your quadratic could have multiple solutions and it still passes through those 2 points, right? Yeah. And this is not just for quadratic, this is for any kind of polynomial. So you could have a bunch of these equations, so something like this: y1, y2, y3, so on till yn. That's equal to this matrix 1x 1x 1 squared all the way to x1 power n minus 1, and then 1x2 x2 squared all the way to x1 power n minus 1, and so on, right? xn stuff, and this time c0 c1, so on till cn minus 1. So if this determinant is non-zero, you can find a unique degree n minus 1 polynomial, and there you go. Nice. So that's it. I'll see you guys in the next video.